Okay, welcome to this lab on inventory simulation and optimization. The goal of this lab is to give you a base that you can use to build your own simulations and also to show you what are some of the nice things you can do with simulation that are usually difficult to do with writing out the math equation and trying to use calculus to find the minimum of some cost function. Especially if you're doing it in a closed form solution type of way where you want an equation like an EOQ equation to give you the best ordering quantity which gives you the lowest cost. So the math approach has some limitations. If you remove the limitations, the math becomes really complicated, and simulation allows you to remove those limitations and still not get very complicated and still get your results. So that's what we're going to try to learn today. So I'm not going to have you write too much code. I've written most of the code. I'm going to explain it to you. I want you to understand it and then how to make small changes to adjust it for your situation. Okay, so we are going to simulate a pretty straightforward reorder point system, which is also called continuous review system. Okay. And so basically what happens is you have R, which is a reorder point. When your inventory position IP becomes R or lower, you place an order, a replenishment order with your supplier or with the factory. Right, you place a replenishment order. And how much do you order? This tells you when to order, right? When to order. When do you order? When inventory position reaches R, then you place a replenishment order of size Q, okay, which is sometimes called the EOQ quantity. And then once the order arrives after a lead time L, right, then your inventory position will jump up. The plus Q will increase your inventory position when the order arrives. Okay. And if there's demand variability, you have safety stock built into this R formula. So R is going to be demand during lead time plus the safety stock. That's the expected demand in lead time, right? So safety stock is built into the R. So it's also called like a safety stock system. So let's look at the Python sheet. Okay. Now I'm going to talk through and explain the code and explain some basic building blocks of simulations. You want to think about any coding problem. Okay, anything you're building. What is sometimes called a data-driven design. Okay, so you want to think about what is the data you need to accomplish whatever you are accomplishing. This data would be composed of, there'll be some inputs. So you need some inputs to work on. In the case of the simulation, you can't really do anything unless you know about the demand. Because you're going to simulate demand coming in, you're going to simulate this pile of inventory, and this will decrease, the demand will take away from the pile. Then replenishment will happen, this will increase the pile of inventory and so on. So you have to simulate this process day by day, demand coming in, eating up your inventory as being sold, right? Think of a warehouse that's shipping out product for customers. And then when the inventory runs low, you reorder from the supplier, you get a replenishment, inventory goes back up. So that's what you're simulating. And a demand we are going to simulate over a year, so you can add seasonality, right? We know that for a lot of consumer goods, demand goes up in the last quarter of the year because people do a lot of shopping around Black Friday, Christmas. In your country, it might be some other holiday, Chinese New Year, things like that, right? And so you could put a seasonal pattern in your annual demand, and then what happens? Well, your inventory runs out much faster during the high selling season. So to simulate all that, we need some inputs, right? We need to know demand, okay? We need to know about replenishment, how long it will take to replenish, right? And things like that. And we can set this, we can generate this data. We can generate a demand pattern at random. We can generate demand pattern with seasonality. We can set a lead time of a week and see what happens. If our supplier is far away overseas, we can set a lead time of 8 weeks, right? So we can do all those things, and we're going to specify that as our inputs to this program. Then another type of data is called state. Okay, state is what does the program keep track of while it's running. So while it's simulating, it needs to keep track of the inventory position, because how does it know when to reorder for replenishment when the inventory position falls below the reorder point R? Okay, so the state is going to include inventory parameters, reorder point Q that we are testing right now. We're going to test the simulation with multiple values of the inventory parameters. So the inventory parameters, inventory position that we are tracking, the orders we have already placed with the supplier that may be on the way to our warehouse, how many days left in receiving an order, right? What is the quantity that we order for these orders? A lot of information is state we have to keep track of while we run through the whole year to simulate a whole year with our inventory policy and with a certain type of demand. And then actually we also have to keep track of costs, because at the end of the year we want to say with this demand pattern and this inventory parameters, we ran a simulation for a whole year, and that's what's going to cost you. That's what's going to be the inventory cost. And we can rerun this for some other value of the inventory parameter scale, get another cost, and then we can compare across the costs to see which values of the inventory parameters minimize the total cost, right? And then maybe a third type of data you need to keep track of is outputs, which is what does the user want to see when the program finishes? Does the user want to see the inventory position for each day of the year? Probably not. The user wants to see like some statistics on the cost, like what was the total cost? Okay, how many lost sales did you have? Like when you ran out of inventory, how often did that happen? Maybe the user, right? And the user also wants to see what were the inventory parameters you used. And maybe they want to see something like total demand. Okay, how much was the total demand and things like that, right? And so you have some inputs, you're going to have some state while the program is running, you have some outputs. That's the data you're going to need for the system. And then you can think about, when you have thought about the data, how are you going to process the data? Okay, so in our case, we'll have some sort of a loop that runs day by day. Okay, so what do we do each day in this loop? So we have this loop that loops over days 1 to 365, so of 1 year. Okay, and in computer speak, this will actually be 0 to 364, because in computers we start counting from 0. So day 0 is basically your day 1, 1st of January, and day 364 is December 31st. Okay, so we think of it in our head as day 1 to day 365 of the year, but the computer may count from 0 to 364. That's still 365 days. That's 365 different values. Okay, then each day what happens? So each day, the first thing that happens in the day is, okay, we receive replenishment orders. And you might be like, well, that's not going to happen on day 1 because I didn't place a replenishment. Yeah, but when the loop is running, you can't just think of day 1. You think of any day in the year. What can happen? Well, you could receive a replenishment order. Receive replenishment orders that were ordered L days ago. L is your lead time. So if your lead time is 14 days, any order you placed 14 days ago will arrive today. Okay. What you can also do, let's say your lead time is variable. So each time you place an order, it gets assigned a random lead time. So maybe your lead time varies between 10 days and 20 days. So it sometimes takes 10 days, sometimes it can take 20 days. Usually takes someday in between 10 and 20 days. So then you would have to go through all the open orders and see which one the time is up and I need to receive it now. Okay. But if all orders take L days, like the lead time is fixed, then you just go and see where L days have already happened. Those orders need to be received. What does receive mean? That's going to increase your inventory, right? So if you receive an order with 500 units, your inventory should jump up by 500 units. Then the second thing that should happen that day is that you satisfy the customer demand for the day. So we get the demand for the day, we get the demand from some demand generation process, right? So usually we call a function to generate the demand for that day, and we pass in which day of the year it is, because the demand could be higher in certain months, right? And so this function, the demand function, will be written to capture our demand pattern. The easiest way to think about the demand function is you have a 365 demand values from, let's say, the past year, where the demand was the last year, or you have generated those values based on expected patterns, like a forecast. So you have a forecasted value. It's just a table in Excel, and this function just goes to the row for that day, picks up the value from the Excel table, and sends it back, right? So it says, here's the demand for day 10, here's the demand for day 11, here's the demand for day 12, and on and on and on, right? So we get the demand for the day we are currently on, okay? Because we're looping through all the days. So in the first time to loop, day is going to be day one. Then second time is going to be day 2, day 3, day 4, like that, right? So we get the demand. Then number 3, we try to satisfy the demand. Try to satisfy the demand. Why do I say try? It is possible that your demand is more than the inventory you have. And it is possible that your demand is less than equal to the inventory you have right now. Not the inventory you've already ordered, because that's not there yet. That's still with the supplier or on a boat somewhere, on a truck somewhere. You can't satisfy demand with it. But the inventory on hand right now. So if your demand is less than inventory on hand, you just reduce the inventory by the demand value. So you say, okay, my demand was 20 and I had 100 pieces in stock. So my stock now went back to 80. And then you say demand satisfied, or demand supply, or demand satisfied total for the whole year. That will increase by demand because you've satisfied that demand. Okay, and so you're good, right? You satisfied the demand. But what if demand was bigger than the inventory? Okay, then you'll only be able to satisfy partial demand. So the partial demand will be satisfied. What part? You'll give it all of your inventory, because your inventory is less than demand. So demand was, let's say, 20 and you only have 15 pieces on hand. So you give the 15 pieces of demand to the demand. So you satisfy 3/4 of it, but 5 units of demand were left unsatisfied. And then you keep track of lost sales. So you say lost sales were gonna be will accumulate the value of demand minus the inventory in this case. So if demand was 20 and inventory was 15, 5 units of demand was not satisfied. They are lost sales. You lost those sales. The customer went somewhere else. Said, I'm not going to you. I'm not going to wait. And then you had lost sales. Okay. So that's the third thing you'll do. Number 4, because after satisfying demand, your inventory may be too low, check the reorder point and place replenishment orders. So here you'll check if your inventory position is less than equal to the reorder point. Then if that is true, okay, add new order to orders list, right? You have to have a list of orders you've already placed that have not been received. Because what can happen is that, let's say, if you have very high reorder point, you fall below the reorder point and you place an order. It's going to arrive after 2 weeks. Okay, so that gets added to your inventory position. Your inventory position now shows you have an incoming order. But even with the incoming order, after 2 days, your inventory has fallen so much lower that you need to place a second order, because even if the first order arrives, it will not be enough. So you place a second order. So there are cases when you have very high reorder points that you can place more than one order at a time. You can have multiple orders outstanding, one arriving in 5 days, one arriving after 10 days because it was placed later, and one arriving after 14 days, it was just placed. So you could have 2 or 3 orders in the pipeline. So you have to keep track. You have a list of open orders, right? So if inventory position is less than the reorder point, then you place a new order. And notice that inventory on hand is not the same as inventory position. Inventory on hand is the physical inventory you have with you. So if you walk around your warehouse and you count the units of there, that is inventory on hand. Okay, that's the physically available stock. Okay, but inventory position is inventory on hand plus orders that are placed but not received. Orders placed but not yet received. Okay, and minus any booked inventory. What is booked inventory? We're not going to have it in this simulation because it's not, that common. But sometimes you have a customer and you don't have something in stock and they say, I will wait. So keep this inventory for me. So let's say you got a demand of 20, you had 15 in stock. The 5 that you don't have, you book it for future. So the customer doesn't go away, but you're going to give them 5 units in future. So any inventory that comes in future, 5 of that is reserved for this customer. 5 will not really go on the warehouse shelf. They'll just be taken off and shipped to the customer right away. So that's not going to increase your inventory on hand when it arrives because that's already booked for a customer, right? So we're not going to have this in this simulation just to keep things a little bit simple. So this is like 0 for us always. So just inventory on hand plus orders placed. But in some situations, this can happen. Okay, and one thing I forgot in the beginning, actually step 0, before we receive any orders, we have to advance time. So each day, or you could do it at the very end. You could do it at the very beginning or at the very end. We advance. What does it mean to advance time? All the outstanding orders, they have a time, they have a clock on them. Okay, this order was placed on day 1. It's going to arrive on day 14. So you want to decrement the clock. Okay, there's not 13 days left before the order arriving. There's 12 days left, 11 days left, 10 days left, 9 days left, 8 days left. So you do a countdown. So each order you place with a supplier, each time you go to the loop, you have to decrease the time left. Okay, and that way you will receive that way when the time hits 0, you know that you have to receive the order. Actually, it's part of the receive function. In the receive function, you go through and you decrement the counter, and any of the orders which are at 0 time, which means they should be arriving today, you receive those, right? So it's part of that. So you advance time here. Outstanding orders, you have to decrement their counters each time through the loop, because after n days, you're supposed to have time left 0, and then they arrive at your door, right? Okay. So that's how you loop. And then once you're done with the year, you can calculate your total cost because you've been saving your costs in some data structure. And then you can calculate your total costs, right? And then you can add it to a big table. So let's say table row 1, I set my Q reorder quantity to 50. And I set my reorder point to, let's say, 70. And I get a whole bunch of data. I get my total cost here. And this was, over 1 year of simulation. You could do 10 years, 5 years, whatever. You need to do over a long time period, right? So that you get a good estimate of the cost. And then I rerun this simulation. I rerun this whole loop again. I rerun the whole loop, and then let's say I make Q go up to 60 and reorder point is still 70. And I get a total cost. And then I rerun the loop. Let's say, now I start changing R. So I go back to 50, but then I make this 90. And then I go back and then I keep this 50 and I make this 100. Then I make this 60 and I make this a 90. So I go through all possible values of Q and R, and I run the simulation for a year or 2 years or 5 years or 10 years. I get the total cost. If you're running it for 10 years, divide it by 10 to get an annual cost. You can compare on an annual basis. And then you can see, okay, where's the minimum total cost here? Okay, where's the minimum total cost? Whichever row has the minimum total cost, those values of Q and R are optimal. Okay, so what goes in the costs? Because this is the fun part of the simulation. You can model so many different costs and make it a very realistic scenario. Okay. So obviously, you're going to have inventory holding cost. Okay, and this comes from the inventory on hand. So at the end of each day, whatever inventory on hand you have to pay the holding cost for one day for that much inventory, right? Because in calculations, we usually do holding costs per year, but here we're going to advance the simulation a day at a time. So each day of holding inventory, we find out exactly how much it costs to hold the inventory on hand in inventory for one day, and we accumulate that over the year. So you have inventory holding cost. You have ordering costs. So this is incurred each time you place an order, either place or receive. One of the 2 points, you can accumulate that, right? You're going to have lost sales costs. Anytime you're not able to meet the demand because you annoyed the customer or you lost the customer, there's some goodwill loss, there's loss of profit because you couldn't make the sale. So you have some lost sales costs, right? Anytime the demand is more than the inventory, this happens, right? Okay. Then number 4, you could add, I didn't add it in this simulation, I assumed it's part of the ordering cost, because oftentimes we put transportation cost in the ordering cost. If you can, it's not very accurate, but you can also have, this transportation cost. And I'm going to show you how you can modify my code a little bit to do this, where depending on the order quantity Q, you split that order quantity over trucks. So let's say the Q is 500. Okay, you're going to place an order for 500 units, okay? And let's say our truck, one truck can fill 200 pieces. So an order of 500 will fill up the first truck, that'll be the 200. It'll fill up the second truck. Oops, trucks are supposed to be the same size. Okay. It'll fill up the second truck. Okay. And then it'll fill up half of the third truck because 100 is left because this was 200, 200, and this is 100. So it'll fill up just half of it. So this could be a full truckload shipment, FTL, full truckload shipment, FTL, and this will be an LTL for 100 units. So the transportation cost for FTL, you might know, okay, it costs this much. Maybe it costs you $100 to ship a truck, or I don't know, $1,000 or whatever. Let's say it costs you $1,000 to get a truck. So you do $1,000 times 2. That's your cost of the 2 full truckloads. And then you're going to have some way to calculate the LTS cost. It's going to be a function of the 100 units times some rate based on distance, times something based on weight. But you can, talk to your transportation people and get like an approximate formula to estimate the LTL cost for how many units you have. Okay, but what happens sometimes is what if you're doing LTL and your truck is, let's say, like 70% full? And this is you're doing LTL. Because LTL is more expensive per unit, at some point 70 or 80 or 75 or 85%, at some point it's just better to just pay for the full truckload. And it's going to be cheaper than paying LTL for like 70 or 80% of the truck. So you have to calculate this, then you have to calculate, this is transportation cost 1, and then you have to calculate transportation cost 2, which is going to be, assume you ship everything by LTL, that's going to be 1,000 times 3. And whichever is lower, that's going to be your transportation cost, okay? And you can add that to the ordering cost because that transportation is to fulfill that replenishment order, to make the replenishment order happen. So it's good. You could just add it as ordering, or you could keep a separate 4th type of cost called transportation cost and add it to that, right? But notice how we can model real life. We can figure out how many full truckloads we need, how much units will be in the less than truckload, what will be more expensive, to have some full truckloads and an LTL, or to have all full truckloads, right? And then we can calculate the very accurate real life like cost and keep track of it. You can't do that in the inventory cost calculation formulas that you have been taught. Okay, and so that's how our simulation would work. Okay, so before we start the simulation, let's look at the situation and what would happen with calculation. So we're going to simulate a case where our daily demand on average is for 10 units. Let me just verify that's the numbers I have in my code. Yep, 10 and 4. Okay. And the standard deviation of daily demand is 4. Holding cost, it costs $10 to hold 1 unit in inventory for 1 year. That's capital H. Okay. So what does it cost you to hold a unit in stock for a day? Just divide this by 365. So each day it costs you $0.0274 to hold 1 unit in inventory. Ordering cost is $100. Each time you place an order, you incur $100. Lost sales cost is $25. So the loss of goodwill, the loss of the profit from that sale that you were going to make, all that sort of stuff. It costs you about $25 if you have a lost sales. Lead time is 7 days. So the annual demand is just going to be 365 times daily demand, because let's say we're a warehouse, people can order online from us any day of the week. We're like an online retailer, so we don't have the weekends off and things like that. So that's the annual demand. So we just apply the EOQ formula, which is 2 times capital D, the annual demand, times the ordering cost S divided by capital H. And we get a value of 270. So inventory optimization formulas, the EOQ would tell us we should be ordering 270 units each time we order. Okay, so what should be a reorder point? When should we order? Well, that depends on the cycle service level. What service level you want to have. Notice I did not have to pick a service level in my simulation, because I simply keep track of lost sales. Okay, because the higher the cycle service level, the lower the lost sales. So these inventory cost calculations are not optimizing over the service. They're not telling you what's the optimal service level. They're just saying assume a service level, let's say 95%, and then it's optimal to have this reorder point. But if you want fewer lost sales, you go up and you get a higher reorder point, but then you have lost sales. But these formulas are not able to see the trade-off between lost sales and the inventory holding cost, because the higher the reorder point, the more the safety stock, the more the holding cost, right? It's not able to factor that trade-off in the calculation and tell you, hey, given that assuming you've calculated the lost sales cost correctly, you've factored in the goodwill loss or the marketing damage you have, this is the optimal service level and this is the optimal reorder point. It's saying, well, you figured out the trade-off between lost sales and more safety stock, and then tell me what the service level should be, and then I'll tell you the reorder point should be, right? So it's not even optimizing across all 3 parameters, because your 3 parameters are how much to order, EOQ or Q, when to order, reorder point, and what level of lost sales to sustain, like basically how much safety stock to have. And it's not really optimizing across the 3rd parameter. It's saying, you tell me the service level. Okay? So let's calculate the reorder point for 3 different values of the service level. Let's say 95% service level gives me this Z-score using norm.SRINV function. Right? These are just basic inventory calculations you've probably studied in prior supply chain courses or other supply chain courses. In any way, if you're rusty, you can email me and I can send you some slides on the EOQ formula and the reorder point, and you can review them and see how these calculations are done. So depending on the service level, our reorder point is going to be 87, 91, or 94. Well, this will be like 95, 94.6, 92, or 87 or 88, right? So that's what calculation tells us. Okay. So this is the setup. We're going to simulate this first, just like this, and then we're going to do some extensions. Okay. So today we're going to do the first extension, add seasonal demand, because what these inventory formulas assume, seasonal demand, what these inventory, the formulas, they assume throughout the year the demand has, that's a very terrible drawing, sorry. they assume that the demand has a stable level, has a stable mean of 10. In our case, we said it's 10, right? We said it's going to be 10. And then it has a standard deviation sigma around the mean, which is 4. So it just goes up and down, plus minus, 1 or 2 standard deviations around the mean, but the mean level stays 10. But we know very few products sell like that. So we're going to add seasonality. We're going to say the year has 4 quarters. You could do it monthly seasonality too. I'm just doing it quarterly here. So quarter 1, quarter 2, quarter 3, quarter 4. Okay, the demand starts out as low in quarter 1, the average level. Obviously, there's variability around it, right? Something like this. Then quarter 2, it increases somewhat. Quarter 3, it becomes the mean value for the year, about 10. Okay. And then quarter 4 is very high, somewhere up here. And maybe it's like averaging around 16 or something, whatever the seasonality. And then it falls. So this might be a common pattern for consumer goods or things used as gifts or holiday gifts like clothing, right? Where a lot of sales happen in the holiday season or like back to school sales in September, but then, a lower amount of sales. Maybe here is averaging 5, maybe here is averaging 7. Instead of 10. So lower level of sales happen in the first part of the year. Obviously, this is winter close. It might be reversed. You might have a high sales in the first and fourth quarter and then like really low sales in the second and third quarter. Right? So the pattern could be reversed, but the point is your product will have some pattern, and this is a lot better model for how the sales of your product go than flat across the whole year. This is very unrealistic. So what we're going to do is we're going to add this seasonality. We're going to make a more realistic demand model and see if the values the simulation gives us saves us any money over the values these formulas give us. Right? That's an interesting question to ask because these formulas can't handle this seasonal pattern. So does the simulation have any advantage? Does it help us save any money by incorporating the seasonal pattern, which is more closer to reality? Okay. That's one extension. The second extension we're going to do is we're going to say, well, the order quantity Q and R should probably not be constant throughout the year, right? For this case here, up here, well, okay, reorder point R and Q can be the same throughout the year because your demand is the same, right? But in this case, with the demand seasonality, we did calculate an R and Q that works, on average for the year. But what if we allow it to vary, go up and down? So we vary, we get a different R and Q for each quarter. So quarter 1 has an R and a Q, quarter 2 has an R and a Q, quarter 3 has an R and a Q, quarter 4 has an R and a Q. Okay? And we see if varying R and Q saves us any costs. Because, your sales are so high in just one quarter, that's going to lead to a high reorder point. But for the rest of the year, it doesn't make sense to have so much safety stock in January and February when your sales are low, because the safety stock are calculated keeping December into mind, right? And so if you could lower the reorder point and lower your safety stock in January, but then make them go up again in maybe October, November, that'll save you cost. So how does varying the reorder point in Q work? And then the third extension we don't add, but I show you how to do it and you can do it on your own, is this transportation thing. How do you calculate true transportation costs, calculate how many full truckloads you'll need, how many partial truckloads you'll need, and build that into your simulation to get an R and Q, which is optimal not over ordering cost, over holding cost, over lost sales cost, and over transportation cost. It optimizes all of these costs, whereas calculation was only optimizing over these two costs. It is not optimizing over lost sales cost. It is not optimizing over transportation cost. It is not optimizing over a changing demand pattern, only doing it for stable demand patterns. So much limitations with calculations that simulation will help us get rid of and do and handle more real life situations. Okay, so now that you understand the logic, what we're trying to do, the code is going to make a whole lot more sense to you. So let's go over it, okay? So, as always, we just import some Python packages. So NumPy, we're going to use, it has a random number generator, so we need the NumPy package. Pandas uses NumPy anyway, so if you import Pandas, you're going to be using NumPy anyway, but we need to import it like this. So I can call np.random. To generate random demand. I'm going to talk about data class shortly. It's a nice feature to have. And this is optional. I'll show you what it does, but time, you need to keep track of how long it takes to run a simulation, so we'll use the time for that. Okay. So that's just, you've seen it before. You import packages to be able to call built-in Python functions. And if any of this import fails, you need to do pip install here in your book. So you'll do pip install like NumPy, right? But NumPy is already installed, right? So maybe let's say you think, oh, data classes is not installed. So this is the package name from data classes. So you could do pip install data classes, right? And then you can pip install whatever you need. To restart the session. Right, it says already satisfied, so it already has data classes. So I know that all of these packages are already there. You don't need to install anything, but in case in future Google Colab changes, I'm just going to comment it out. What you do is, you get rid of this commenting character and just type !pip install and the name of the package you want to install, and then you can type another line pip install something else, and then you can install any packages that are not already coming with Google Colab, but all of these are. So you don't have to install anything. See, this cell works. If there was one of these packages was missing, you get an error right here saying it could not find data classes or could not find time or could not find typing, right? Okay. Then we have our inputs. This is not just data, like the input data. Okay, they are our inputs that we need. We need this information to simulate. So these are flag variables. Initially, I'm not going to have demand seasonality. I'm going to just simulate the base case. Okay. So that's just a false. QR seasonality is changing the queue, the order quantity, and the reorder point season to season. So that's also false. These are part of the extensions. So I code them in, and then I just turn something on and I run the extension, right? The simulation with modifications. So the demand statistics, mean standard deviation, inventory cost rate. This is the cost per day. So $10 per item per year is how much it costs you to store 1 unit of the item in your warehouse for a year. So 10 over 365 is going to be the rate per day. Ordering cost is $100 per order. Lost sales cost is $5 per item. Lead time is 7 days, right? So you can see all of this stuff is just this stuff right here. Okay, and just H is divided by 365 to get this number, right? That's all the inputs are right coming from right there. And then seasonality factors. If you have 4 seasons for 4 quarters, they should add up to 4. So you can see 0.5 and 1.5 give you 2. And then 0.9 and 1.1 give you 2. So total is 4. 0.5 means demand is 50% lower than the annual average for the whole year. 0.9 means demand is 10% smaller than the annual average. It's 90% of the average demand. 1.1 means demand is 10% higher than the average. 1.5 means demand is 50% higher than the average. So for any period of low demand, which is because it's relative to the average, so if you have lower than average in one period, you must have higher than average in some other period. That's how the seasonal factors work. Where 1.0 would mean average. If the demand was exactly the annual average here, just do 1.0. That means the average. Okay. And so make sure if you have 4 seasons for 4 quarters, these numbers add up to 4. You can easily check them. Let's just add a code block and let's run this. Okay, and you can just do sum of quarterly seasonality factors. Okay, and see that's 4. If you have monthly seasonality, you will say monthly seasonality factor, and you'll have 12 values here, 1 for each month. Okay. And then what am I gonna save in my results table? See, I showed you somewhere here. We save this table. We save QR and all sorts of costs, so we can then find the minimum cost what parameters give us the minimum cost. So you have to generate this table. So I need to know what do I need to save in that table. So I'm going to save the reorder point, the order quantity, the total demand that I simulated, total lost sales, the fill rate, which is what percentage of total demand was satisfied. It's basically total demand minus lost sales divided by total demand. That's your fill rate. Lost sales cost, TC means total cost of lost sales, total cost of ordering, total cost of inventory holding, and then the total cost, which is the sum of all of these. Okay, so I'm going to save all sorts of costs. I'm going to save my parameters. I'm going to save some total demand. Okay, I'm going to save all of this stuff. So then I can look over the results at the end and see, okay, where did which ROP and Q values gave me the lowest cost. So this is just very simple Python code, just saving all the input data into variables. What you can also do instead is you can make a data class here, which I'm going to show you next. Data class are ways to group related data together. So I could say class input data, okay, and then I could say all of this, that my simulation time is an integer, dimensionality is a true false value, and then I could save all these values into input data. Well, what's the difference? Well, then you can say, okay, then once you do that, you can say input data, you can initialize it, and then you can access this as this, demand seasonality, input data dot inventory cost rate. Because all these inputs are related to each other, you can club them into a class which kind of groups them so that you access them through the class. So you say input data dot something, inventory dot something. Now, I didn't do that here because our inputs are about like 5 or 10. But sometimes in complex simulation, you have hundreds of inputs. So you have parameters about your factory, you have parameters about the trucks, you have parameters about the demand. And then it would make sense to have all the parameters about the demand saved in a demand class, input demand data. All the parameters about your factory saved in, input factory inputs or something class. So you group them logically. So if you see something like a certain cost, like a production cost rate, well, is it applying to the factory? Did some production happening in the warehouse? Well, oh, it's in the factory class. This is about the factory, right? It helps you keep track of what means what logically. So classes, data classes especially, not classes in general, data classes are a way to group related data together, okay? So the way you can think about it is, you know how you have in real life, you have forms. So let's say you're a patient, you go to a doctor, they make you fill out a form, so this has your name on it. Okay, it has maybe your address and maybe your phone number, okay? Now, if you're going to work with this data, we know that these three things are related by patient contact, right? Patient contact. That is what the form was called, patient contact form. So just like if you didn't have computers, you would have the patients fill out these forms and you put them in some filing cabinet, right? And so now we want to model this with computers and data. So instead of just having all the names stored in one list and then all the addresses stored in another list, but then you have to know which name goes with which address, so you have to keep them in the same order. That's very cumbersome. You want to group these together so that the name, the address, and the telephone for a patient always stays together and grouped. So you can make a data class by doing @data class in Python. All right, add data class, and then saying class patient contact, and then you can have name, address, telephone, and this just keeps these values for a particular patient grouped together. So when you have patient P1, you can do P1.name to get their name, P1.address to get the address for the same patient you got the name for, and so on. So it groups together different variables into a unit just like a patient form does or any form does in real life when you fill out forms. It groups together that data from the same person or the same entity. So you group together different data about the same entity into one group, and then you access with a dot notation the name of the entity that you instantiated. So you say, okay, I need one patient, I need two patients, and then for each one you can access dot name, dot address, right? So that's what data classes do. So if you have a lot of input data, you want to group related input data into its own data class, and that can be useful. Okay. And then here I do that for orders, right? So whenever I place a replenishment order, it needs to have a quantity, how much did I order, and how much time is left. Like, that's like the status of the order. If I place it today, and my lead time is 7 days, then time left is just 7 days. But tomorrow, time left will be 6 days. The day after, time left will be 5 days. So time left will go down. And then when the time left is 0, then I know, okay, I can receive the order. So instead of saving quantity and time left into separate areas, I just club them together as a class so that each order's quantity and time left are together, grouped together, and I can, access them easily in my code. So that's all I'm doing here. Okay, then, so the first part was for a simulation, you need to have some input data, right? The input data. And what are you going to store as results? Okay. Then you want to have some generator functions which generate the demand for you. Often in our inventory simulations or supply chain simulations, we're always interested in matching demand with supply. So we're always interested in demand. So I wrote this generator function. This is a helper function here. So let me add some comments. So get seasonal index function to convert a day between 1 and 365 into a quarter. Okay. So what I basically do is I divide the day by 91, because if you divide the year into 4 equal parts, you get 91 days, 91 days, 91 days, 91 days. You have 1 day left over because that's 364 days, but we're going to add the last day to the last quarter. Okay. Now in Python, and I know I need 1 to 365 because actually when I do my simulation, I do go from 1 to 365. So I know that computers by default go from 0 to 364, but just to keep things like, as is more commonly done in real life, I just made the counter go from 1 to 365. You can see my time goes from 1 to 365 plus 1 because the last value is not included. The range function will give you 1 to 1 minus whatever you pass it. So if you give this, like if I just call range 365, I'll get 0 to 364. But I'm saying give me range 366, 1 to 366, so it gives me 1 to 365. I'll give you 1 less, this range function in Python. So I'll get 1 to 365 because sim time is 365 right here. Okay, anyway, so I'm going to get a day between 1 and 365, and I need to convert it to a number between 0, 1, 2, and 3. 0 is quarter 1, 1 is quarter 2, 2 is quarter 3, and 3 is quarter 4. So we have this thing in Python. Let's say you are on day 30. You could do day divided by 91 and see what it gives you. It's going to give you 0. This double divide. And if you do day percent 91, it's going to give you 30. So what's happening? The percent sign gives you a remainder. So if you divide 30 by 91, the remainder is 30. But the regular divide will give you a fraction, 0.3. But double divide will give you the quotient, the whole number part, and without the remainder. So that'll give you just 0 because there's 0 and 30 days is the remainder. What if you go to day 135? You should get 1 because that's the second quarter. It's over 91. And there's going to be some remainder, but we don't care where you are in quarter. We just want to get the quarter. So that's 1. At the end of the year, you'll get 3. So your quarters, the 4 quarters are 0, 1, 2, and 3. The only problem is day 365 gives you 4, which gives you the 5th quarter, because So we have to, if it's above 3, just make it 3. That's the last day of the year. It gives you a higher quarter number, right? Quarters are 0, 1, 2, and 3. Remember, last day of the year will give you quarter value of 4, which must be mapped to 3. Else, we will have 5 quarters in the year, which is obviously wrong. Okay? So we just divide by 91, and if it's less than equal to 3, we just pass on 3. But if it's 4, the minimum function will pick this 3, because it's going to be the minimum of this value and this value. Okay, so that's useful function to convert the day of the year into the quarter that it belongs to. Then I have a demand generation function, which takes the day of the year and gives you demand. Now, if demand seasonality is false, it's just going to return a random number with the mean and the standard deviation of demand. Okay, so it's going to be this situation here where demand is stable throughout the year. No matter what day you are on, it's the same mean and standard deviation, just generate a random number around that mean. Okay. But if the demand seasonality is true, then first we get the seasonal number. Then I use this seasonal index to increase the average demand up or down by multiplying by it. So I multiply the mean demand by the seasonal index, so the demand goes up and down. And usually when the demand goes up or down, the variability also increases. When the demand doubles, it's also going to vary more than it used to. So I also increase the standard deviation by the demand seasonality to be more realistic. And then I generate the random number for this increased or decreased demand. So I've changed the demand mean and standard deviation based on the season. And then this season-dependent mean and standard deviation is used to generate random demand in this function. Depending on this flag, if this flag is true, the seasonal index will be incorporated. If the flag is false, this will not be incorporated. What this allows me to do, I can just toggle this flag and rerun my simulation, and I get seasonality built in. I don't have to recode. I don't have one code for no seasonality, then write another code for with seasonality, and a third code for this. My code is flexible. It can handle these scenarios depending on which flags I turn off and on. Okay, so that's how I'm coding, thinking about what I need. Okay, then if we do want to adjust a base reorder point and a base queue for the different seasons, now you have to think about how you're going to adjust them. I'm just adjusting them in proportion to the seasonal factor. So if my seasonal factor is 0.5, my demand is half of the usual. I make my order quantity and my reorder quantity also half. But it's technically it should not be linear. The order quantity should go with the square root. So I should do I should have a square root here somewhere. So if my demand doubles, my Q increases by 1.4, because square root of 2 2 raised to power 0.5, that's a square root, is 1.4. Okay. So most likely you need some way to adjust your base R and Q for the different quarters. And that's going to impact your cost. So I'm doing, and to me it makes sense to kind of maybe the reorder point is going to be adjusted like this, because this demand, the standard deviation is proportional to the demand standard deviation, and the standard deviation is proportional to the seasonal factor. So this is correct. The reorder point is correct, but this one should probably be a square root in here, and you can do that and read on the simulation and see if it gives you different results. That's the good thing about simulation. Okay, what if I do this? Well, just do it and test, right? I could just do this. I could put a bracket and do a square root raised to power 0.5 and read on my simulation, and with a square root, maybe I'll get the same result, maybe I'll get a different result, and I can see if which adjustment is better, right? So I'm just keeping it linear right now. Okay, so these functions will tell me which Q value and which ROP value to use depending on the day of the year. Now, if the seasonality adjustment is turned off, it's just going to be the same value as the base value, right? But if the seasonality is turned on, then I'm going to adjust the base value for the season I'm in, based on which season I'm in, and that's based on the day. And then I'm going to return the seasonal adjusted Q and the seasonally adjusted R. So again, just like demand, depending on the flag, either you just return the default value or you return the seasonally adjusted value. Okay, now we need to handle our orders. This is the only part which is a little bit complicated about this code. So I'll spend some time explaining it, because the issue has to do with if your reorder point is very high, you can end up in a situation where you need to place multiple orders, right? A lot of simple simulations you'll find online, they'll just have the support for one replenishment order at a time. If you've placed a replenishment order, you cannot place another one until you receive it. But that can be incorrect because, look, I'll show you. Let's say this is my reorder point R, okay? And this is my inventory position. It falls below. This is my IP. And this is also my inventory on hand because there's no outstanding orders, right? IP is inventory on hand plus any outstanding orders. So there's no outstanding orders right now. As soon as this falls below, I place an order for size Q. Let's say my Q is not that big. This is my order. This is Q. So I place this order. Well, what happens if you place Q? Your inventory doesn't go up because you don't receive the order right away. It's going to come after 7 days. So your inventory continues to fall, but your inventory position is now up here, right? Because inventory position is including the Q that I've ordered. It's going to be higher than the inventory. Okay, let's say this is when I place the order. Okay, this is some day. Let's say this is day 4, and on day 11. My order is going to arrive, day 11, okay? So as my inventory keeps going down, on day 11, the order will arrive, and this will jump up by Q, right? This is Q, inventory on hand. My inventory position falls again below the reorder point, so I need to place another order here. Because inventory position cannot stay below the reorder point. Whenever it falls below the reorder point, you have to place an order. So even though my Q was small, my ROP is very high, even though I did place an order before, even that order is not going to be enough. Because look, when you do receive that one order here, look, your inventory is still too low. So you place another order. Okay, maybe this is like day 6. So on day 6 plus 7 is 13. On day 13, we'll jump up by Q again, inventory on hand. This will be the second Q2 will be received. And so as your inventory position hits this, you keep reordering, right? And you could have at one point in time 3 or more orders in the pipeline that you've ordered and not received. And then they start arriving day 11, day 13, day 15, they start arriving tick, 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 right? And then your inventory starts to go back up, inventory on hand, right? As the orders start to arrive. So this situation can easily happen, especially if you have a high reorder point for some reason. And in simulation, we are going to simulate over a big range of reorder point values. So it could very well be that in a simulation, our values are all wrong because we never allowed for there to be multiple orders in the pipeline. And so you have to simulate, you have to have a pipeline of orders. You have to allow for multiple orders to be in the pipeline in inventory simulations. Okay, that's just a must if you want to do things the right way. So to make the code simple for me, okay, the code for simulation, this code here is simple. I put the logic of an order pipeline, we have a pipeline of orders and then orders get received, into this class here, okay? So the init function, you have 2 underscores, define underscore underscore init underscore underscore, and takes self as a parameter. Self refers back to itself. This function will initialize any values, any data in the class. So anything you see in the init function is data that the class is going to hold. So I have orders, which is a list of type order. So this data class which has two parameters, this group of data. I'm going to have a list of that. List means I can have, 1, 2, 3, I can have multiple of that. In other words, in real life type of terms, you see this patient contact form. You have a folder where you can put in multiple patient contact forms. This folder is called a list. And what is the list going to store? A list means I can have like multiple of them. And the thing I'm going to store in this folder is a form of this type. This is my form with quantity and time left. And then I'm also going to keep track of the total pipeline inventory I have, which has been ordered but not received, which is the total of all the quantities in this list. Right? So if in this folder I place 3 forms, I go through the 3 forms, I add up the quantity 1, quantity 2, quantity 3, that's the total quantity that's in the pipeline. That's going to be saved in this variable. The 2 underscores before a variable name means it's a private variable. So only the code inside this class can look at this variable. The code in some other function like here, it cannot look at this internal variable. It's like internal is hidden to the outside world. Okay? It doesn't have to be that way. If it's confused, you can just take out these 2 and just make it like this. Okay. But good code design, we need to make it private because this is an internal record keeping for this pipeline inventory module. Outside the pipeline inventory module, we might give them this information through a function, but not directly mess with this. Because if some other code was to change this, and this did not correspond to the list. So if the list had 3 orders in there, and somebody went and increased this order quantity, and there's no order in the list, then your world is falling apart. Your data is not matching each other anymore, right? So you could have errors like that. That's why I want to keep it private. I don't want anybody outside this class to mess with my internal state for the class. I have a placeholder function that takes a quantity and a lead time that will make a new form of type order, a new object or a new form, a fresh form, fill it up with this quantity that's been passed in, fill it up as time left is going to be the lead time, and then append this new form to this list, add it to that folder. And when you add a new form to the folder, you have to increase your internal state, which keeps track of how much quantity you've ordered. You have to increase that by the quantity that you just added. Okay. Then you have an advanced time function, which takes an argument of delta, how much time to advance. When you have a parameter like that, you say equals something, that's a default value. So if I just call advanced time without any parameters, the delta will take a value of 1, but I can specify a different delta. In this simulation, I only need delta 1. I always advance time day by day, but in different, if you're doing a simulation per week and you have demand per week, you want to advance it by 7 days, or in other situations you might advance it by multiple days. Okay, so I loop through all the orders in my list, and I decrement the time left by delta. Minus equals means basically, it means time left equals time left minus delta. So this long line here, the shorthand is minus equals. It means subtract that and then save the result in the same variable. Okay. What's called the self? The self is because you can have multiple lists. You can create multiple objects from this class. So each object will be a new folder. So you can have folder 1, for certain orders with supplier 1. You can make another folder to place orders with supplier 2 in here, right? So you can have multiple of that. So when this code is run, it needs to know, okay, which folders am I going to operate on? I'm going to operate on folders for supplies in Asia. I'm going to operate on the folder with orders to Europe, right? Which data I'm going to operate on. The self ties the code and the data together. The self variable tells this code, okay, work on that folder and go over the orders in that folder. So it's automatically passed by Python when you call this orders.advanced time. You don't have to pass in self here. Python keeps track of it, but we need the self. And then we call self.orders to work on the right data in the right folder. Okay. That's why when you use classes, you have all this self variable all over the place, but it's just linking the code, because Python doesn't want to save if you have 3 folders, it doesn't want to save 3 copies of the code. That's you wasting memory in your computer. It's going to save 1 copy of the code and just connect that code to whichever data the code needs to work on. And that's done via the self parameter. Okay. Okay, so it passes on the self parameter to the code, and when the code access anything as self dot, it's working on the folder that is assigned to it. Okay. Okay, so for advanced time, we loop over the order in self.orders, all the orders in the folder. We take them one at a time and they get assigned to this local variable order, and then we set their time, we subtract the delta from their time. To receive orders, okay, we are gonna sum the quantity of all the orders for which time left is 0. So ideally you should do time left equals 0, but if you were to do delta of 2, let's say you advance time by 2, then you might have some orders which arrived on day 1 and some which arrived on day 2. So the time left for day 2 will be 0, but the time left for day 1 will be -1 because they've been waiting on your receiving dock of the wares for a day. Right? So we want to allow for the possibility it was weekend, you were closed, so some order arrived on Saturday morning, but it's been sitting on the dock for 2 days, and now on Tuesday you're going to actually put it in your warehouse. So time left on the order can go negative if it's arrived at your warehouse and just sitting there in the parking lot or something, right? So I want to allow for that possibility. So I say if time left is 0 or lower, I take all those orders and I sum the quantity. This is called a list comprehension in Python. And this is not the time to explain it, but basically it's a for loop. I could do the same thing in a for loop and say for order in self.orders, just like that. And I would have a variable here called quantity. And I'll do if time left is less than or equal to 0, quantity plus equals, order.quantity, and I could do this in a loop. This list comprehension is just a shorthand way of writing a for loop. This is just the same logic as this loop. It would have an if condition in it to check for time left, and then based on the if condition to sum them up. So I can just do it quickly in one line here. If it doesn't make sense, you can just write a for loop yourself. But all I'm doing is I'm going through the list of orders, and for any order where the time left is 0 or negative, I add it to received quantity. Then I have to delete the orders that I've just received because I have received those quantity. I delete those orders from the list. Okay. And I do that by making a new list for only the orders where the time left is still positive. So a subset of the old list, I make a new list and I assign it, I overwrite the old list by the new list. Okay. Then I have this internal variable. What is the outstanding pipeline inventory quantity? I need to subtract that because I've received this quantity. It's coming out of the pipeline. So my pipeline has less inventory now. Pipeline inventory is reduced. Pipeline inventory is inventory on the way that's not yet received. So I subtract the pipeline inventory to account for the orders received. And then I return the received quantity. Tell them this is the quantity you just received. So add it to your inventory on hand. So when this is returned, the code which called this function will add it to the inventory on hand. And then if the outside world wants to look at how much is the pipeline inventory, I give them this function to look at this variable because it's private with a double underscore. So they can't write to it, they can't modify it, but they can read it using this get function and see what the pipeline inventory is. This is going to be useful because we're going to calculate the inventory position. Remember, inventory position IP equals inventory on hand plus your pipeline inventory, right? The inventory which is the ordered inventory you already ordered. And this we're going to do get ordered quantity function to read this value. We can't write to it directly, but we can read it to this get function. Okay, so that was the logic of having a pipeline of orders in your simulation. And then we're going to go over, okay, how do you, this is very easy. Just go through each day of the year in a loop, and you just check each day is the demand less than inventory, demand more than inventory. You do these 4 steps. Okay, these 4 steps: receive orders, get the demand for the day, try to satisfy the demand, check if you need to place a replenishment, this stuff basically in a loop. So that's pretty straightforward. Okay, so now that we have understood the orders pipeline that is implemented with this logic, we can get to our main simulation loop. Just make sure all this code has run, so the Python interpreter knows about all these functions and classes. And so this is the loop where we do those 4 steps. Okay, so the function first sets the internal state to 0. and it creates the list of orders, which is going to be empty to begin with. That's going to be an empty object of this type. That's going to say, that's going to, you know, keep our list of orders that we place. Okay. And then because we're simulating for a year, we don't want startup effects. Like if you start with zero inventory, you may have very low inventory for the first few weeks or something, and then that can affect your cost calculations. So we start off with average inventory level, which is going to be Q over 2. So whatever our Q we are using, which will just be the base Q if there's no seasonal adjustment for the Q, or the seasonally adjusted Q, we'll set our starting inventory to be half of that. So if you're ordering, let's say 250 units at a time, you'll start off with inventory 125 on hand, because that's the average cycle inventory. Okay. This is not that important, especially if you're simulating multiple years. Let's say you run a simulation for like 5 years. Starting inventory being 0 is going to have a very tiny impact on the average cost over 5 years, because it's going to be non-zero for most of the 5 years, right? So the longer time period you have for your simulation, the less the starting state matters. But I feel it's still reasonable and good to set like a more realistic starting state than have inventory start with inventory 0, because usually you have some inventory on your hand when you start the year. Okay. Then we go over days 1 to 365. The range gives you 1 minus the second argument, the second parameter. So if I pass it 365, it's going to give me up to 364, which is fine if I make this 0. So I could go to 0. So an alternative could be, I could say range 0 to same time. Same time is the final day of the year, 365. So 0 to 365 would actually give me 0 to 364, but I want to go 1 to 365, so I pass it 1 here, and then this is 366 because I did a plus 1, and it'll give me 1 to 365. Okay. Those are my days. So I loop over the days. Obviously, if you want to do 2 years, you'll just set sim time to be equal to 365 times 2. If you want to do 10 years, just set sim time equal to 365 times 10, or 3650, right? So you can set sim time to be whatever number of days you want. You can say be 100 days if you want, but you want to do at least a year and a multiple of a years. Okay. So the inventory on hand, we start off with something, but then in the loop, the first thing we do, that's our step 1, is to receive orders. So we call the orders pipeline to give us any orders that has arrived. Obviously on day 1, because we never placed any orders, no orders are there to arrive. So inventory on hand will stay what it was. But as you go forward in time and the loop goes on and on, this would return you a quantity based on this logic that we already coded up here. Okay, it will return you the quantities of all the orders on which time left is 0. Then we advance time, so all the orders that are outstanding, their time left gets reduced by -1, so that next time in the loop, some of them may have arrived. Then we generate demand with our getDemand function. We pass it the day, which is the time index, because the demand could depend on seasonality. In the base case, it will not. So if we turn the flag off for seasonality to false, then it will not depend on seasonality, the day. But in the general case, it can depend on the day. And we already coded the generator function up here to generate the demand based on the demand mean and standard deviation. Then we set Q sold to 0, how many we have sold on this day, and then we're going to calculate what Q sold is. Okay, we calculate inventory position. Okay, that's going to be inventory on hand plus the pipeline inventory, which is we get from get ordered quantity right here. Okay, so we add the pipeline inventory to inventory on to get inventory position. Then we check, because we may have to place an order for that, we need the inventory position. Then we check the demand for today, which is in D, saved in D, with inventory on hand. You never compare demand with inventory position, because inventory position includes inventory that's on its way. If it's on its way, you can't give it to the customer today, right? So you only compare demand to inventory on hand. If demand is larger, which means you have a stock out, then you can only sell what you have and your inventory on hand goes to 0. But if demand is equal to or less than inventory on hand, then you sell the entire amount and inventory on hand gets subtracted by that. Now we'll use the inventory position to do step 4, which is checking if you want to place a reorder or not. So if inventory position is less than the reorder point, again, I'm not hard coding a reorder point here. I'm calling a function to give me the reorder point for the season because I want to allow for the reorder point to vary for different seasons. If inventory position is less than the reorder point, then we place a new order by calling orders, which is our list, which is our pipeline right here, which was created right here by creating an object of this class. We call its place order function with the order quantity Q. Again, because Q can vary by the season, I'm going to get it from get Q. If I'm not varying Q, it's just going to give me the base Q value, and I pass it the base Q value. Okay, and the base Q and the base R values, the QR parameters are given to my simulation function because I have to simulate for this time using these inventory parameters. They're passed in as parameters to the function. So I'm going to use the same value for Q unless I'm adjusting Q by season, right? And the lead time is going to pick up the lead time from the constant defined up here, what the lead time is. Okay. And then whenever you place an order, you have to increment your ordering cost. And because we had a demand of D, we increment our total demand because we're keeping track of it. Our lost sales become D minus the quantity sold, which will be 0 for the most part because Q sold equals D. But sometimes when demand exceeds inventory on hand, then Q sold will be a smaller number than D. And in that case, the lost sales number would go up. Then we calculate the lost sales cost, which is each lost sales has a $25 penalty. So we multiply that by that. And we calculate the inventory holding cost using the inventory cost rate for each day. Then this is the end of the loop, right? So this is the end of the loop because see, this is indented inside the for loop. Now when we go back to this level of indentation, now we are at the for loop level outside the for loop. So this is outside the for loop. So after we've done a whole year, by loop through the whole year, done these steps, receive orders, update inventory on hand, generate demand, fulfill the demand, check if you need to reorder or not. If you need to reorder, place the reorder, and then update your costs. When you've done these steps in a loop 365 times through the whole year, then we calculate total cost, so the holding cost, lost sales cost, and ordering cost. We calculate the fill rate, which is the percentage of demand that we're able to satisfy. And then we create a new row by giving it labels. So reorder point is going to be R. Actually, it should be base R and base Q. So the base R and base Q pass to this function. Okay. R would also work within this loop. We define R and Q here. So they would be the same as base Q and base R, but it's a little bit better coding to call it base Q and base R. Because R and Q are also defined here where I call this function, so that will still work. But anyway, total demand and all of the costs, we make this a row in our table. Remember this table we talked about where we're going to save all of our outputs, our results. So we generate a row of this table and then we return this row. So the whole purpose of this function is to run simulation for a year or multiples of years depending on the sim time passed in, and then return a row that'll go into this results table that'll have a value for our Q, a value for reorder point, and then all of the costs associated with that. So each row tells us if you were to have whatever demand generation process you have specified and you were to have this value of the inventory policy R and Q, this is what your cost will look like based on simulation. Okay. And then we want to do this for different values of R and Q. So we generate possible values of reorder points. We know that the reorder point is not going to be less than a day's demand. Even if your lead time was like 1 day, you need to have at least 1 day of demand left in your inventory before you when you reorder. So the minimum the reorder point can be a day's demand. So we start with at 10. And the maximum a reorder point can be is a whole year's demand. Usually you're not going to have safety stock equal to 1 year of demand. So that's 360 times daily demand, about a year's demand, a little bit less. So that's the maximum theoretical range where the reorder point can be, right? A day's demand versus a year's demand, somewhere in between that. And then we take steps of 20 because checking for each value of the reorder point is going to take too long, because for each value of the reorder point, we have to loop over the values of the ordering quantity, and then for each of that, we have to run the simulation for a whole year. You can, if the simulation runs too slowly, you can increase this to, you can reduce this one maybe to like 250 or 300, or you can increase this to like 25, 30 maybe. Okay. I would rather reduce this because I know my reorder point is not going to be like a year's demand. It's probably going to be maybe 2 months demand, 3 months demand, 20 days demand, right? So this is overkill. So you could just reduce that if the simulation is taking too long to run. Make it go down to 250 or even 200, okay? Then you want to time how long it takes. So we say start time is time.time. Okay, then you set up a progress bar, okay? Which is we get the progress bar from these widgets that are built into Python, and we just display it. Then we set random seed. So if you run the simulation multiple times, you want to have the same values of the demand generated, because we want to change queue and test what is it with our different queues. We want the same demand. If the demand also changes and queue also changes, well, maybe this time you just were lucky and you got low demand or something, or high demand or something, right? So although over a year it would cancel out, some days you get higher demand, some days you get lower demand, but still it's to have replicable results in simulation, it's usually a good idea to set a seed value. Seed initializes the random number generating function, and if you initialize it to the same value, you get the same sequence of random numbers out of it, right? So usually it's the norm in simulations to set a seed value. So if somebody else runs a simulation, they can replicate your results and get the same outcomes, okay? Then we go in a loop. We loop over the reorder points. Each time we loop over a reorder point, we increase our status bar, and you'll see it when I run it. Let me run this code so I can run this. And then you run the simulation, you get a new row, you append the row to a results list, and then at the end, when the simulation is done, you stop the timer, you convert the results row to a data frame, and then you find the optimal policy, which is the results with the lowest total cost, and then you print that policy, and then you print how long it took. So let's run this simulation. Let's make sure everything is false. The base case, no demand seasonality, no adjusting inventory parameters for seasonality. Okay, so as you can see the progress bar running through. So it takes a while. This is the good news is it's running on Google servers. So it's running on this virtual machine, which has like 12 GB of RAM, has a reasonably powerful processor. So it's not going to store on your computer. You could go and like work on a project or report or write an email while this happens, and it's not going to store on your computer. So here we go. So without seasonality, we got reorder point of 10 and queue of 20. So if we compare with our calculations, okay, our calculations EOQ was 270, the Q was 270, simulation gave us 270. Look at that. Okay, so saying you can keep the same queue. It gave us a higher reorder point. Do you know why? Because lost sales are expensive. It wants to avoid the lost sales. It's saying inventory holding cost is not that high, have a slightly higher reorder point, don't have lost sales. Whereas, because this Excel formulas can't optimize over the trade-off of lost sales versus holding cost, it doesn't optimize that trade-off. It's just saying you pick how many lost sales you want to have, and then I'll tell you the reorder point, right? So that's first. So what I want you to do, because you're going to have to submit your Excel file, you can, with a table like this, what I want you to do is copy these results to a table, okay? So the table is going to have this. So this is the baseline case, okay? We got ROP of 110. We got Q of 270. Okay, our demand was this. We can just copy paste that, total demand. Okay, and we can take out the decimal points. Okay, then our lost sales are 0, lost sale cost is 0. Obviously, if there's 0, failure is 1. Ordering cost is 1400 and holding cost is this. I had a different seed, so that's why they're slightly different, but you can say they were very, very close, right? And then total cost was 2939. So see, almost exactly the same. So that's our baseline. Okay. Now we're going to save this 110 and 270. So when we do have demand seasonality, we can compare, if we had not done the simulation and just used these values, this is a simulation without demand seasonality. So if we use this optimal parameters and our sales in reality has demand seasonality, what will be the cost? So we're going to do that next. So we can save these. We can also save these. So we know what that is. Okay. So now let's run the simulation. So if we don't have demand seasonality, these are the optimal values according to simulation, which differ. Okay. Which differ from what the calculation gives us. If you look at the 98% service level, let's look at an ROP of 90, so about 90. Let's see what the cost would be if we use the calculations. So we can go back, set reorder point to 90, okay, which is what the calculation gave us, and set Q to 270, which is what the calculation gave us, and see for 90 and 270 what our cost was. And our total cost was 3387 using calculations. So, so even when we don't have seasonality, okay, calculations using this parameter from calculation, the very high service level, 98%, okay, we would have ended up with a cost of 3,387, but simulation gave us a better cost. Why? Because this calculation is not optimizing the trade-off of lost sales versus holding cost, and this simulation is. So even without demand seasonality or more realistic considerations built into the simulation, even if reality is simple and demand is flat on average, simulation still saves us money. Okay. Now let's see if demand is seasonal. Okay. What happens? So we go back to our simulation and we just change this flag. And you have to do this. You have to make this column just like this. You have to have your total cost. You have to have the total cost using calculation parameters, params. Okay. Which is right here. Actually, let's move this lower. Sorry about that. Delete. Okay. Okay, so this row is going to have what would the cost be for this scenario, this column scenario, if you use the calculation. And the cost would be this much. Okay. Now we're going to have seasonality, and we're going to see what happens if demand is seasonal. And so we have defined these seasonal indexes up here in the input data, which tells us that Q1 sales are low, Q2 sales are close to the mean of the whole year, Q3 sales are a little bit higher than the mean, Q4 the sales are much higher than the mean. So that's the seasonality pattern. You could change the pattern and try different ones, but this is what we are trying for, like a very consumer good which sells well in the holiday season type of thing. Okay, so we're going to set the seasonality flag to true, and then rerun the simulation and see what are the optimal values now. Okay. Meanwhile, let's calculate the cost saving. So if you were here, if you could be at 2,900, but you end up being here, what's the percentage cost difference? So the cost of not doing simulation in this scenario, how much can you, that's going to be this minus this, okay, 448. And that means if you divide by the calculation cost, how much can you go, what percentage are you going to save by doing the simulation relative to the calculations? Your costs are going to drop by 13%. Okay, just, and this is without using the realistic seasonal demand. Just even if your demand was flat, and then which is the assumption of the calculation. So even in a reality where the assumptions of the calculation method are correct, I could shave off 13% of my inventory cost, which is a decent chunk of money, because this is just for one product, right? So you go through all products, just by optimizing the lost sales versus holding cost trade-off, which simulation does for you, and that calculation does not. Now, obviously, there's more complex calculations which calculate the optimal cycle service level, which try to optimize this trade-off. And if you do those more complex calculations, these would match. You'll not have a savings here. But the point is that you have to increase the complexity of the calculation more and more and more as you try to match real life. Whereas with simulation, it's just very easy. You just turn on a flag in the simulation or change a line of code a little bit, and then you can bring that thing into the simulation, right? And most people are doing this, right? And then they're leaving money on the table. Okay, so let's see what happened with seasonality. I already ran this last night, but I'm going to update these numbers with the new seed I'm using because I changed the seed just now. Okay, so I got 130 and 370. With seasonality. Okay, let's look at our costs. 1,000 ordering cost, and then 2265. Let's copy this. Okay, and total cost is here. Okay, so let's find out if we use the calculation parameters, which were 90 and 270, what would our total cost have been with demand seasonality? So we're going to look up the row in this table. Remember this big table we made for each value of Q and for each Q and R period gives us the cost. So we're going to look for what would the cost be if we use 90 and 270, the parameters by the calculation, and look at the total cost. That would be massive, above 7,000. And then the cost of not doing simulation, the savings is this minus this, okay, divided by this. So if you were to go by calculation and then you switch to simulation, you'll be saving 56% of the cost. From 7,003 you go to 3,000. So imagine, see, demand seasonality shows up in so many products. And so with all that seasonal demand out there, using these inventory formulas, you're losing so much money on the table. You're not optimizing your inventory, which is why it's so powerful just to know some programming and be able to do simulations. Now, what if we were smart enough to do simulation, but we didn't do simulation properly? Our simulation did not factor in demand seasonality. It only did the baseline type of simulation. So we got these optimal values. What if we use 110 and 270? Okay. So let's another code block. Let's copy this and here do 110 and 270. Then our cost would still be pretty high, but not as high as using calculation. Okay. So doing so with baseline parameters, these parameters stuck into a seasonal situation, you can see that you still keep losing money in the table. You can reduce the cost about 50% by making sure your simulation factors in the seasonal demand pattern, which is why I love simulation. This is to assume, okay, to assume that your where did I draw here? To assume this scenario, that your demand is flat over the year, is just so unrealistic. And inventory calculations assume that, that you lose so much money on the table, you don't optimize your inventory. But when you start to have simulations with more complex and more realistic demand patterns, like a seasonal pattern, you can see how much money you can save. And that is why people are always fighting inventory, because the inventory calculations just don't give them, a good result. Okay, so you see how much money you can save if you build the right simulation with demand seasonality. Now let's see if we can, go below. This cost is using these parameters which were calculated factoring in seasonality. So the simulation, looks at that your demand goes up in the last quarter of the year, but it's still not. We're still not allowing these parameters to change over the year. They're fixed to 130 and 370. So even in January, when your sales fall, you're still having a high reorder point for no reason. Let's allow these parameters to vary over the quarters. Okay, so we go back to our simulation and we say, okay, so we're going to allow the QR parameters to vary over the seasons, and let's see what happens now. Can we save a little bit more money? I mean, you're already saving a lot compared to not factoring in seasonality. When you factor in seasonality, you get parameter values that save you a lot of money, about half. But can we do even better? Can we get a cost even lower than this? And notice that your seasonality is going to be a higher cost than if you didn't have seasonality, because whenever there's demand variation, variability influences cost of your system. When you're trying to fight variability, and have stock, you have higher safety stock with this higher variability, you're going to end up with more cost. But the problem is, if you don't model the seasonality, you assume the world has flat demand, you're going to think your cost will be this, but your actual cost will be this, right? So this would be the cost. If you use these parameters values and you thought demand was flat, but demand was not flat, it has the same mean with seasonality. We've not increased the demand. The demand is the same annual mean. It's still averaging 10 a day, but it's just much higher than 10 in December and November and much lower than 10 in January. You still have the same average demand. You think with these parameters you're going to get this cost, or this cost. If you use calculation, you're going to get this cost. You think, but because the seasonality, you're going to get this cost. And with simulation and seasonality, you're going to get this cost. So this is much lower than what actually you get if you don't have seasonality. Okay, so let's see if we allow the QR to vary over the year. So notice our base Q, R, and Q went back. Why? Because in none of the quarters we're going to use this exact value, because we're going to adjust them, right? So our base Q and R went back to that. But if you look at quarter 1, quarter 2, quarter 3, and quarter 4, we multiply them by the seasonal indexes. So your Q is going to be this value times the seasonal index. So your quarter 1 Q will be 55 in this simulation. So it's not going to be one value, right? Your quarter 2 Q will be 99, and so on. Right? It'll change to these values. And reorder point. Your reorder point will be 55, 99, 121, and 160. So you can see that your safety stock is going up and down depending on the variability of demand, because the variability of demand is higher when demand is higher. And so you're adjusting your reorder point. And your Q is also going to vary based on the seasonal index. So you're going to have different Q for the different parts of the year. So I forgot to put F4 here, the dollar signs here. So it was, see, this is picking up the empty cell. So notice so these are your R and Q values in this simulation. This is the base value. It gets multiplied by the seasonal index to get the actual R and Q values that we use. Okay. So let's see what other statistics we got. Demand was this. Okay. We had, a tiny bit of lost sales, and probably that is a function of, we haven't built in the simulation that if you expect a season to change, or let's say you're in the end of quarter 3, so you're in, let's say, October, start of October, no, start of September. So in start of September, you should actually change your R and Q values to start building up the safety stock for October, November, December. But we don't do that. We actually flip over the R and Q parameters at the start of the new quarter, and then you're starting the new quarter with less inventory than you should. You're not being proactive. So you could change the code to look 1 month ahead and change R and Q based on 1 month ahead, what's going to happen next month, and that would give you, no lost sales. But because we are flipping the switch, we got a tiny bit of lost sales. Okay, just less than 1 unit even. On average, so it's like 0.44 means like every 2 years you'll have 1 unit of lost sales, right? About half a unit a year. Okay. Lost sales cost is about $10. Let's see, our ordering cost is $1,500, and then our holding cost is this. And then our total cost is about $3,000. Okay, and so you can see that we saved some money compared to not allowing Q and R to vary. You save about 8%. Okay, so this is the savings from allowing Q and R to vary over the year. So that means having the same reorder point and order quantity for the whole year is not optimal, right? You can save some money by allowing them to vary. And now let's see what the cost would have been if we just use the calculation parameters. 90 and 270, our cost would have been this. And actually I can't do that because I'm varying Q and R, so I can't use this table. So I can't check that because I'm even with the 90 and 270, they're going to be varied over the year, multiplied by the seasonal index. So that's not right. So I can't do the comparison with the calculation here because I'm changing Q and R, and there's no change in Q over the year, and that doesn't change. So I can't do that comparison. But we can see that simulation is compared to calculation. Even if we assume the assumptions of the calculation are true, it saves us 30%. If we go for a more realistic scenario, it saves us 50% of the cost. And if we allow Q and R to vary, it saves us a further 8% of the cost. So a lot of cost savings by doing inventory optimization using simulation. So you have to build this table, okay? And you're going to submit a screenshot of this table with these percentages calculated for your submission for this lab. Okay. So this is the code that I'm going to share with you. Okay. So remember, let me put it here. This is, let's see, cost if using calculation parameters. And this is, let's see, cost if using flat demand scenario parameters when demand is seasonal. So if you calculate your parameters assuming demand is flat but demand is actually seasonal, we can look at that too. So this is what it gives you. You will not run these two cells for the loss scenario when you're allowing Q and R to vary over the year because Q and R are changing, and then this comparison is not a fair comparison. But you will run these two cells when your demand is seasonal, but Q or seasonality is set to false. So I'm going to set these back to false for the base case. Okay. And so yeah, that is the lab. So I wanted to share one last thing I want to tell you about the transportation thing, that we can change the simulation to incorporate transportation cost, because there's a trade-off in transportation inventory cost as well, and our inventory formulas don't capture that, and this is really complicated to capture because depending on the order quantity, how you transport is going to change. Sometimes it's going to be full truckloads, sometimes it's going to be less than truckloads, sometimes it's going to be a mixture of full and less than truckloads. So as you change your queue, try a different queue, the transportation cost calculation is going to get vary. But simulation is not too hard. What you do basically in the simulation is every time you place an order right here, okay, instead of just adding the ordering cost, instead of this line here, okay, what you do is you say ordering, you say transport cost, or okay, you add, let's see, you save a different, let's say you keep the ordering cost as is. If you don't add to the ordering cost, we add to the, we have a new transportation cost. So up here we'll just say total transportation cost equals 0. Okay, and then here, in addition to the ordering cost, we'll update the transportation cost. Plus is equal to transport cost for this time, and transport cost will be calling a function like get transportation cost. Okay, we'll pass it the day, the time index, because transportation cost may vary over the year. You may have higher transportation rates in December, right? So you could be want to incorporate that, and you want to pass it the order quantity, which is given by get q, and get q equals day equals time index, and base q equals base q. Okay, so that's your quantity. Or we already got the quantity here. Do we see? We didn't see. Okay, so yeah, that's gonna be giving you the transportation cost, and you just have to write this function. Okay, and then you can go up here and write this function. Okay. Okay, so it gets time index and day, and then here you'll have something like, you know, number of full trucks. That will be Q divided double slash by the capacity, by the truck capacity. How many units can one truck have? That'll give you the whole number of parts, and then the LTL amount will be the remainder of the truck capacity. So that'll tell you, okay, how much units are left. And then your cost one will be num of full trucks times FTL cost plus LTL amount star the LTL rate. What does it cost per piece? And then cost two will be, you'll just do the extra truck. You'll do everything number of full. You'll just do instead of the LTL, you will add an extra full-time truck, a full truck, and just ship the LTL amount in the full truck too. And then you'll return the minimum, whichever is minimum. So whether it's better to have all full trucks, or you're going to have some full trucks and then one LTL truck, whichever is lower, you'll go with that. Because, you know, LTL shipments, when you get above 70-80% of the truck full, you might as well pay for the whole truck. It's cheaper. And so you will not account for that. So you have a function like this. You'll have to define truck capacity somewhere up there in the input data based on whatever trucks you use, right? And then this way you will be able to model the transportation cost, right? And then you'll to the total cost right here. Then you'll add the total transportation cost right here, and then you'll minimize the total transportation and the inventory cost, right? In your simulation. So we're going to take that out. You could do it on your own. But this is how you would do that. So very easy, just a few short lines, and you can build in, the transportation expense. I'm just running it to make sure everything runs properly. Yes, everything is running properly. So everything is fine. Okay. So that's how you would update it to factor in that. So you can see simulation is so powerful. I can have seasonal demand incorporated. I can have the trade-off between lost sales and holding costs incorporated. I can incorporate the transportation cost expense, which will go up as you order higher amounts. And if you and you can incorporate complex patterns where you change Q and R differently for different times of the year. You can incorporate look ahead where you change Q or R, depending on what the future looks like. You could build all that sort of logic in and figure out how to optimize your inventory. So this is really cool. So I hope you enjoyed the lab and hope you were able to make this table, and you can submit a screenshot of that, put it in a Word document as your submission for this lab.